Okay folks, this time I'm just going to show some of the equations I've been using and some generalized information about the two isotopes I've been studying, the iodine 131 and the strontium 90. Okay, you got your Z for half-life, your P for continuous output, your Y for initial output, your Z equals Z units minus P units, where the largest number of units must be reduced to the smallest units, and D is the amount remaining. The original equation is D equals Y plus P by Z, all that minus 1/2 times Y plus P times 1 minus 1 over Z plus 1 minus 2 over Z plus 1 minus Z over Z. It goes all the way out to ever how many Z's you're using. The secondary equation, the D1 equation I call here, it's where you don't, where if Y was not available in the original equation, then you would substitute 0 for that Y, and then the next time you go through for the next 30-year or half-life period, say strontium, then you would put the answer from the previous equation for the half-life, which would be this one up here. Then you, or if you were looking down here, you can easily see what I'm saying here. See, it doesn't have any of that included in it. This is the simplified version of this without the Y. Okay, if you don't have the initial amount, then that right there is the equation you use. It looks almost identical, except it doesn't have the Y in it. Once you get this equation completed, you substitute its answer D into for Y up here, and it makes the D, as you can tell, the D replaces the Y all the way across. And for a strontium 90, if you're measuring in hours instead of years, you're talking about, in this case, 788,400 hours in its decay pattern. Now that 30 there came from this figure down here, the 500 figure of sieverts per hour from reactor number 2. Well, we go down here to this figure and we find out strontium 90 has a 6% existence rate, meaning 6% of the nuclear byproducts from the fission is going to be strontium 90. So 6 times 500 is 30. Well, actually 6 divided into 500 is 30, which gives you that equation there. And then I multiplied that out just so you could look at it. As you can tell, it goes into the tens of millions of units will have been produced just in the first 30-year output at that sievert level per hour. Now this information over here, I didn't fill that out because that's 192 equations. Plus there's two equations per each item, so I didn't bother to fill that out. Well, actually, it's more than that. I was thinking about the iodine. That's the strontium. Oh, good Lord. 788,400 equations. Not without a computer. With a calculator and hand doing it, no way. Then you got iodine. You see similar numbers. It's in days for the, well, it's actually in hours, but that 192 is hours in an 8-day period, which is its half-life. The 15, again, here for iodine, you got 3% is the available rate in the nuke byproduct. So it has 3% of the nuke byproducts are usually iodine 131. So you got 15 times that. It's only comes up to 2,880 units, which ain't really all that bad. Of course, it goes down a little bit when you fill in this part right here, because that subtracts from it. But it might half it if it does that much to it. As you can tell, D is in sieverts per half-life. So that's, in that 8-day half-life, you got 2,800 sieverts minus whatever that comes up to. And up here in strontium, you got 23 million minus that amount, whatever it's going to be, is your 30-year total. So that's a lot of numbers. And for some references, you got Seeker on YouTube. His post was on a title of "The Internet is Overreacting About Fukushima Radiation. Here's Why." February 12, 2017. RT America, another YouTube channel. Title was "Radiation at Fukushima at Highest Level Since Meltdown." February 6, 2017. And that reactor number 2 there, 73 sieverts were measured in 2011, which is the year the accident occurred. But by 2017, the sieverts had went up to 530 in that reactor. So that's a significant jump. And then you got this guy over here, which thanks to him, I was able to do some stuff that I probably wouldn't have been able to do. MBYE-News. That's his YouTube channel, and his title was Fukushima Radiation Wind Causes Poisoning Countries Globally. Wikipedia is what he was showing on there. He was showing a thing from Wikipedia, and the percent of radioactive particles that were coming out of the radioactive byproducts was 3% of the uranium was letting off a iodine, which I also listed back over here. And thanks to him, I knew that Wikipedia would have that information, so I got it from strontium 90. I was unable to get it for cesium 137, so I didn't include it here. Maybe someday they'll list it, but if they don't, oh well. Well, that's pretty much the sum of it. As you can tell, them were some big numbers. But that strontium's over a 30-year period, so it's not that big of a deal. But the point I'm trying to make is this equation predicts how it will grow and eventually slow down in growth. But there is a point where it'll be so slow in declining that it literally won't decline at all for all practical purposes. It'll get down to, let's say, like 5,300, then 5,450, then 5,525, then 6,000. It just slowly gets slower and slower with the number of units remaining after all the half-lifing, the decay, and the addition of the additional radiation coming from the continuous output, which is P here. As you can tell, there's 30 additional outputs going per hour times the number of hours per 30-year period. That's not that bad, really. Then when you look at this one right here is only 192 hours long, but it's 15 sieverts an hour. Half as many sieverts per hour, but over a much shorter time period. That's the reason the numbers are so much smaller. So they decay fairly rapidly and will disappear more rapidly. But if there's always a radiation source, then that will be constant. It'll be constantly putting out that 2880 plus whatever's out there that hasn't half-lifed away yet. And that's what this equation here is about. This one right here, shown here, is to estimate how much has decayed during the period from the end of the last half-life to the end of the next half-life. Well, that's it. You guys have a good day.